Hello everyone. Now we will talk about our final linear algebra project, speech and audio separations. It was made by Stanislaw, Ivan Rudish, and Stanislaw, Ivan Shynkarenko, and Arthur Rudish. So let's move on. The agenda of our presentation is here. Firstly, we will talk about our aim and motivation to do this project. Secondly, about main approach and the um, linear algebra methods. Third and fourth, Ivan will be talk about data description, implementation, result, and benchmarks. So, description. What is speech separation? Speech separation is task to isolate two voices from a mixture from the mixture audio when it can be used. It's when it's multi-speaker environment, it's when noisy settings, and when it's forensic analysis. So, our motivation and aim to do this project. The primary goal of our project is to develop a solution for speech separation. It could be a software where you input an audio signal with mixture two voices, two audios, and after that you will have two individual audio signals when you have separately first speaker and second, or it will be more about audio as you wish. So our motivation is because we wanted to go deeper into understanding of matrix factorization because during classes we learn about QR factorization, SD factorization, and also we wanted to open for our minds and other types of factorization. We find non-negative matrix factorization and its use, and it was very interesting for us because uh, machine learning now is developing very fast and it's very interesting marketing to go to work. So I think our motivation is clear. So main approach, as I said, our main approach is non-negative matrix factorization. But firstly, to factorize our matrix, we need to apply short-time Fourier transform to our audio signal to convert it to a magnitude spectrogram. Nextly, we give this magnitude spectrogram to our function, which is called non-NMF. It's using iteration decompose our magnitude spectrogram to two individual separated matrices, matrix V and H, using Kullback-Leibler divergence. It's like minimize the difference between our matrix V and the multiply of our matrix W and H. And after that, we make source reconstruction by inverse short-time Fourier transform. So what is non-negative matrix factorization? As I said, is to decompose our matrices V by two matrices W and H. In the first matrix W is a basis matrix. We show our signals, and H is show coefficient. It's more about to talk about sources of our signals. And what we need to do, we need to decompose our matrix V by such matrices that their difference will be as small as possible. For it, we use like 4 and 4 to 4 Bius distance or KL divergence. What is pros and cons of our methods? It's like interpretability. It's like to the V and H components often have a clear physical meanings, spectral features and their time activations. It show us where specific signal were activated during the time period. And it's more simple because there are another methods like ICA. It's more difficult for us to understand for us to understand it, how it works. But matrix factorization was easier, so we decided to use this method. But also it has cons. It's like the optimization problem is not convex, which leads to a local minima. And choice of rank sometimes can be difficult for us because it's not always the number of sources, the number of channels, and we need to find the best this rank of matrices by ourselves. Next, Ivan will talk about our code, but firstly, I will show you a pseudocode of our function. First is like interesting thing that W and H are firstly randomly fooled, and nextly, iteratively, we find the best fit for them. To multiply it, we'll have the minimum distance from V. Ivan will start now.
Here's our okay. Here's our code. It is non-negative matrix factorization.py. Here we use such import numpy for heavy lifting, matplotlib for plotting, and librosa for short Fourier transformation. Here we are dealing with initialization. Instead of a random start, we use SVD to get the leading singular vectors and build non-negative W and H by decomposing subsequently singular vector into positive or negative parts, picking whichever piece has larger energy. The smart init often speeds convergences and avoid poor local minima, especially on outdoor spectrogram. Then here is calculating cost. We support three cost functions. The first one is Frobenius. The second one is KLD, which stands for Kullback-Leibler, which is popular for audio magnitude spectra, and IS, which stands for Itachi-Cito. Okay, here is our speech non-negative matrix factorization. So firstly, we're checking in our loop with which function we are dealing, Frobenius, KLD, or IS. Then here is our numerator and denominator. And as you can see, in each iteration, we are updating H and V in W. So we make an renormalization of each of them, and then here is our function negative matrix factorization. After factorization, we still have run components, but want to recover num sources and separate audio tracks. Here we use a frequency centroid clustering. For each component column of W, compute the weighted average frequency and sort them, then chunk them into equal sized groups. Reconstruct each source spectrogram by summing only its assigned sub component. And we are returning the list of source spectrograms plus the row of W and H and assigned array for just for debugging. Then about the spectral difference. Okay, so here again saying imports, and it is used actually just for helping. Like this helper computes a mean absolute difference between the magnitude spectrogram of two signals, great for a quick frequency aware distance metric. We first stream the signal to the same lens, run short Fourier transformation on both, take magnitude, then average the absolute beam by beam difference. And okay, and that's it.
So, as Ivan said, is our implementation. And on the left side of my screen is you can see our database. The first is our data for our IP Y and B, and the next is like to test speech separation. So thank you for attention. We think our project will do the best onto the presentation. Thank you.